Hey everyone, welcome back to my channel. The question that I'll be solving today is minimize all of remaining elements using operations. And it came in LeetCode Weekly Contest 382, and this is the last one. In this question, you will be given nums and it is okay. And you can pick any index I and you can replace nums of I as well as nums of I plus 1 with a single occurrence of and or both the elements and here represent the bitwise and you need to find the minimum possible value of the bitwise or of the remaining elements that you will have in your array now because you will be replacing some elements with the and operation now. What are the elements you are having in the nums? You need to replace, you need to return the all of those elements. Now let me make you understand. The key concept over in this question is nums of I is less than 2 to the 30. So if you are moving from the 0th bit position, we can go far up to 29th bit position in the binary form. So for each bit position, we need to check whether I can put 0 or not because our goal is to minimize. If we can minimize our answer by placing 0, that's the only possible way. If we try to put 0 in every bit position, whether it is possible, if it is possible, then I'll put 0 and I'll be moving from the 29th bit to 0. Why? Because if I can place, let's say this is the one and 0 on 1. If I can place 0 over here, that's the best thing by placing 0 over here. Because let's say 0 1 0 and 1 0 0 0. This thing is greater. So for the larger bit position, we'll be greedy to put 0. That's our goal. Now, how can I put 0? If some element have 1, let's say at ith bit position, I'm talking about can I put 0 over ith bit position or not? Ith bit position. If some element have 1 at the ith bit position, then I need to perform the OR operation, or not OR, it's AND, with some element having 0 at the ith bit position. That's the only way. So we can form the groups. Let's say I'm 1 then 0 0 0. Let's say this is the element, then I can 1 0 0 0 and I want to perform operation for this. This is the ith position and I want to check whether I can put a 0 or not over this position. Then again 1 0 0. This is a group of having 1 to the ith bit position, and let's say if there is a 0 1 1 1. So I can form a group of this, and this is a group which, if we are performing AND of these elements with themselves, this will result in the 0 at the ith bit position that we want. So we need to form groups of this kind so that the AND operation of these elements would result in 0. And the number of operations required over here is the number of elements minus 1. So 1 2 3 4 minus 1 is 3. Why 3? That's 3. So they can do an AND operation with themselves to get a 0 at the ith bit position. What if there is, let's say 0 1 0 1 then 1 1? This is also a group which can get 0. This is the ith bit position. So this group individually can get a 0 at the ith bit position. So this is one of the group. So operation required is the number of element minus 1. So that is 0. For this also the operation would be 0. If I'm having 1 then 1 1 then let's see. So for this group the number of operations would be 3 minus 1 2. They will be doing AND with each other. So that's it. Like they are doing AND operation with the element at the front, and so on and so forth, up to they are reaching a 0, like element having 0 at the ith bit position. So this kind of groups will be formed. So the number of operation required over here is 2. If 2 is less than k, then I can definitely put a 0 to this position. Like a 2 is less than equals to k, then I can definitely put a 0 to the ith bit position. But how can I check individually for, let's say, 29th bit and then 28th bit? Is it possible, like the operations required to put a 0 at 28th bit position if it is less than equals to k, if it is less than equals to k? How can I do that for each and every bit? Because the total operations there is given as k. That is the main confusion. Like given as k total, that is a total operation, not for the individual bit position. That k is the total operation that we can perform. So if I take an example, let's say this is one bit, then 0, then 1 1. So over here also there is 0, say 1, then 0 and 1 1. Let's say this is I equals to 2. This is our group. So the groups that I'll be forming until I reach a 0. Then again I reach a 0. For this, the operations required will be 2 by 2, because these two elements have 1. Now they have to be AND with some element having 0, either in the front, because in the they have to do an AND operation with some element at the back, because at the front they don't have element. So we are assuming the operations would be 2. For this operation would be 3. Now operation would be 2. For this also 2. Now for if I do for I equals to 1, this is the 2th bit position. And this is the first. Let's say there is 0 1. This will be forming individual group. Then again let's say 1, then again we are reaching 0. So this is one of the group, and let's say 1 1 1 and 1. This is another group. So this is kind of for the first bit position. So this is the binary representation, like the number is 1 0, then 1 1 0. So this is the second bit, and this is the first bit. So this is kind of groups we can form. So we can transform these smaller groups into the larger one. How it is possible? Let's say 0 1 1. This one group is also a group. They, if we are performing AND with these elements like 0 1 1, they also result in the 0th at the first bit position. So we can transform this group in the larger one. And for this 0 1 1, this can also be one of the group, like the above one and 1 1. This can also be group. So this group can do a AND operation with each other, and resultant would be a 0. This is not a group. So the operations required over here is 2, over here also 2, and over here also 2. So I'm saying that if I'm forming larger groups, for larger groups, operations required is more. For smaller groups, operations required is less. So I can transform these smaller groups into larger groups. Transform. And like I was doing 2 to 5 operations with these elements, and I was supposed to have a 0 at the second bit position, and using these operations only, like for the second bit, if I'm using the same operation for the first bit, then I can also have a 0 at the 0th position. At the first position, I can have a 0 at the second as well as at the first. So that's what I'm saying is I need to find the larger groups, like the for the second iteration, for the first bit position, for the zeroth bit position. The one having larger group, let's say the first one having, then I can transform this groups to the second to the first bit positions group, and the zeroth groups to the first bit group, like the smaller into the larger, and the operations required for the first if it is less than k. So these operations, like the larger groups operations, can make zero for the smaller groups operations also, that we have seen in this example. Like for the second bit, whatever operations we have used by forming groups, we can use the same groups to convert zero for the smaller groups, as I've explained in the example. I think it's clear. Let me show the code, it will be more clear. So in the code, first I've taken the num size as n, then I'm traversing for each and every bit from the 29-bit position up to 0. And what is a target? Target is to check the valid groups. Target is answer. Initially answer would be 0 because I'm checking can I place the 0th bit to the 29th bit position or not. So target is answer, or the this is the 0th at the ith bit position, and all the set bit from 0 to I minus 1 bit position. So I'm checking, is it possible to put a 0 at the ith bit position? That's why I have put 0 to the target in the ith bit only, and the answer that is representing from the 29th bit up to I plus 1, and ith bit is set to 0, and 1 I minus 1 to 0, it is a set bit. Now operation initially is 0, and current is to get the and of the groups. Initially it is all the set bits up to 29-bit position. Now I'm doing the current and the element, and then increasing my group. If current or target is target, why it is like target has a 0 at the ith bit position. So if current also have a 0 at the ith bit position, then only it can be equal to target. Current is not violating the answer, like what I have placed before from the 29-bit position to I plus 1. If current is not violating that, as well as it has a 0 at the current bit position, like I bit, then only it's a valid group ending at the current element. So I'm again initializing the current and operation, like it's a valid group, so the number of operation would be group minus 1, that is the size of group minus 1. And again I've initialized the group as 0, then operation plus group. Why it is? Because the last group that I'm left with, which is not a valid group, so the number of operation that I've told before, it would be the number of elements in the groups, so that is the group size. If the operation is greater than k, so I failed to put a 0 at the ith bit position, so I have to put 1 at the current bit position, so that I'm doing or with the answer, and I'll be returning my answer. So the key concept over here is to transform the smaller groups into the larger group, as well as to calculate the target. Target is the previous bits that I have placed, or the set bits up to I minus 1 bit position, and 0 at the ith bit, to check is the group which is not violating my answer, as well as have a 0 at the ith bit position. If it's a valid group, then I'll be adding to the operation and again initializing to 0. So that's it. Thank you for watching.